The design of highway intersections. Intersections are one of the foremost factors of road and highway design. It is the point where the components of the highway mode of transportation converge. Drivers, cyclists, motorists, and pedestrians meet along different junctions. Because of this, intersection designs must be suited for facilitating safety and mobility objectives, which contribute to economic and physical aspects. From Fuentes' famous roundabout, Mambaling's underpass, and to the networks of roads that lead to essential locations, the benefits of highway intersections are undeniable. It presents opportunities to develop public domains, especially in our modern society where connection and integration are at the forefront of progress. Whenever we travel around the city or rural areas, we observe a lot of portions where roads intersect because these intersections provide shortcuts or alternative routes, as well as connect people to their infrastructures, services, and commodities they need to develop and survive. For this discussion, the design of highway intersections will be elaborated in terms of design reference flows from baseline traffic figures, major and minor priority intersections, roundabout intersections, and traffic signal control.
Good day, everyone. Now, before dwelling into the design of highway intersections, we need to have an ample data that will serve as a basis for its design. Now, first, we need to derive design reference flows from baseline traffic figures. Now, what do you mean by this? It means that the sample data is gathered to serve as a reference flow, and these data are gathered from baseline traffic figures. Now, these traffic figures may refer to pedestrians, vehicles, as well as their interactions within the road. Now, first we can derive data from existing junctions. Basically, these junctions are those that have already been constructed. For example, under the overpass, the junction in the N. Bacalso Avenue connecting with the South Road properties as well as the Gotchan Street. We can derive a lot of data from it, especially daily traffic and peak flows. At existing junctions, it will be possible to directly estimate peak hour and daily traffic flows together with all turning movements. Now, recalling what traffic flow is, it is the total number of vehicles passing a given point in a given time. Traffic flow is also expressed as vehicles per hour. Now, moving on, in order for the measurements to be as representative as possible of the general peak flow levels, it is desirable to take them during a normal weekday from Monday to Thursday or even Monday to Friday within a neutral month of April, May, June, September, or October. So why now take the data during neutral months? It is because of the conditions during the season which are ideal. It means that there are no barriers that may affect the data collection. Now, factoring up the observed morning and evening peak hour flows using indices given in the National Road Traffic Forecast, it can lead to the derivation of design reference flows or the DRFs for the design year, which is normally 15 years after the opening. Now, flow patterns and turning proportions observed in the base year can be extrapolated in order to predict future patterns of movement. Now, moving on are the new junctions. Now, these junctions are those that are planned to be constructed. Now, in a situation where a junction is being designed for a new road or where flow pattern through an existing junction are predicted to change significantly, meaning that the flow may not be constant because of the changes to the general network, flows must be derived by the use of a traffic modeling process which will generate estimates of 12, 16, or 24-hour link flows for a future chosen design year. Now, average annual daily traffic flow are then obtained by factoring the 12, 16, or 24-hour flows. Now, recalling what the average annual daily traffic means, it is the average 24-hour volume at a given location over a 365-day a year. The average annual hourly traffic is then calculated by dividing the average annual daily traffic by 24 and then factored to represent the appropriate highest hourly flow using derived factors. Now, tidal flow is also taken into consideration. Generally, a 60 over 40 split in favor of the peak hour direction is assumed. Turning proportions are also guessed estimated so that the junction can be designed. Now, moving on is the short-term variations in flow. Traffic does not usually arrive at a junction at a uniform or constant rate. During certain periods, traffic may arrive at a rate higher than the DRF or the design reference flow, and there are other times where it is lower than the DRF. If the junction analysis for a priority junction or roundabout is being done with the aid of one of the Transport Research Laboratory's computer programs, namely the PICADY or the ARCADY, such variations can be allowed for using a flow profile. A typical profile could involve the inputting of peak time flows in 15-minute intervals. When calculations are being completed by hand for a priority junction or roundabout, such short-term variations may be taken into consideration by utilizing an hourly flow equal to 1.125 times the DRF. In the case of a priority junction, this adjustment should be applied to the design flows on both minor and major arms. In the case of a roundabout intersection, this factored flow will impact not only on the entry flows to the roundabout but also the circulating flows within the intersection. Moving on is the conversion of the average annual daily traffic to highest hourly flows. Appendix D14 of the Traffic Appraisal Manual originally detailed factors linking the average annual daily traffic to the 10th, 30th, 50th, 100th, and 200th highest annual hourly peak flow for three classes of roads, namely main urban, interurban, and recreational interurban. Particularly on urban highways, where peaks are less marked, the 30th highest flow may be most appropriate. On interurban route, the 50th highest might apply. On recreational routes where peaks occur infrequently, the 200th highest may be the value most consistent with economic viability. The general implication is that where the design flow is exceeded, some degree of congestion will result. But this is preferable and economically more justifiable to the situation where congestion will never occur and the road is under capacity at all times.
Now that we have discussed about design reference flows, we will now move on to its implications in major or minor priority intersections. A priority intersection occurs between two roads, one termed the major road and the other the minor road. The major road is the one assigned a permanent priority of traffic movement over that of the minor road. The minor road must give priority to the major road, with traffic from it only entering the major road when appropriate gaps appear. The principal advantage of this type of junction is that the traffic on the major route is not delayed. To put this into context, the Bacalso Avenue that leads to important locations in the city can be considered the major road because it is where most commuters and drivers travel along. In contrast, the Magochan Street that leads to Punta is the minor road. The principle at the basis of the design of priority intersections is that it should reflect the pattern of movement of the traffic. The heaviest traffic flows should be afforded the easiest paths. Visibility, particularly for traffic exiting the minor junction, is a crucial factor in the layout of a priority intersection. Low visibility can increase the rate of occurrence of serious accidents, as well as reduce the basic capacity of the intersection itself. Priority intersections can be in the form of simple T-junctions, staggered junctions, or crossroads. A prime example of the simple T-junction is the road along Shopwise and Metro. For the staggered T-junction, it can be seen in Mountain View and the way to Talavera. Lastly, for Crossroads Junction, it can be seen in Punta where traffic congestion is always present. For the T-junction and staggered junction, there are three distinct types of geometric layout for a single carriageway priority intersection. Simple junctions. A T-junction or staggered junction without any ghost or physical islands in the major road and without channeling islands in the minor road approach. Simple junctions do not have physical, ghost, or channeling islands. Ghost island junctions. Usually a T-junction or staggered junction within which an area is marked on the carriageway, shaped and located so as to direct traffic movement. For ghost island junctions, traffic movement and turning is directed because of the markings. The purpose of a ghost island is stated as to provide right-turning vehicles with a degree of shelter from the through flow. Single lane dualing. Usually a T-junction or staggered junction within which central reservation islands are shaped and located so as to direct traffic movement. Single lane dualing is somewhat similar to ghost island junctions, but it has central reservation islands to partition the lanes. The type or level of junction utilized depends on the flows from both the major and minor roads. The simple layout is appropriate for new junctions in rural locations. The two-way AADT on the minor road is not expected to exceed 300 vehicles, with the major road two-way AADT not exceeding 13,000 vehicles. For single carriageway roads, the different levels of T-junctions appropriate to a range of flow combinations are illustrated in the next figure. The information takes into account geometric and traffic delays, entry, and turning capacities and accident costs. The following figure shows the different levels of priority intersections for various major and minor road flows in the design year. Now, for this example, an existing simple major or minor priority junction at the intersection of two single carriageway two-lane roads is to be upgraded. The major route is a major interurban highway. The figure on this slide illustrates the forecasted AADT flow ranges for the intersection's arms in the design year. Taking the upper AADT flows of 10,250 for the major carriageway and 3,000 on a minor carriageway, a ghost island junction might be an ideal choice. The two-way annual average traffic on the arms can be taken by dividing the AADT by 24, which will produce the following values on the next figure. In this case, the AADT is translated into AAHT. When the economic grounds are emphasized and become the reference for the junction's design, the 30th highest annual hourly flow must be addressed. With regard to the local traffic count data, the AHT flow on each of the approach roads is translated into a design peak hour flow by multiplying by a factor of 3. It will then give the following values. Directional splits derived from local traffic data are applied to these design flows to obtain the final directional flows. A 70 to 30 split in favor of flows from the southern and eastern approaches are utilized in this context. Turning movements were assessed based on the present-day traffic flow data from the junction. The proportions are indicated in the following figure. Taking the upper flow ranges, combined with the turning proportions indicated, a set of flows is derived which can then be used to analyze the junction. Next, we get the final upper range flows, which will be essential in designing the highway intersection. Once the flows to be analyzed have been determined, and a generally appropriate geometric layout has been settled on, it is then necessary to establish the capacity of each traffic movement through the priority junction. In each case, it is mainly dependent on two factors: the quantity of traffic in the conflicting and merging traffic movements, and the general geometric properties of the junction. The traffic flows relevant to the determination of these capacities are shown in the next slides. The streams are described as follows. The QCA is on the left lane going right. The QCB is initially from the right lane and then turns to head on the right lane of the southern direction. The QAC is from the right lane, taking a straight path going west. The QAB takes a not so significant turn heading south. The QBC also takes a not so important turn as it heads west. The QBA is from right of the split lane and takes an important turn to head east on the opposite lane above. Hence, the dotted lines describe the crucial turns. Next, we head to the important equations surrounding capacities. We will just go over this quickly because most of these equations only require plugging in data for the specific parameters. In these equations, the stream capacities and flows are measured in passenger car units per hour, or simply PCU. Here is the representation for the geometric characteristics of junctions for D, E, and F, respectively. These characteristics are specific to each opposed traffic stream. Here are the parameters. Mu is for the stream capacity, while Q is for the flow of stream, and the subscripts merely indicate the part of the intersection where the flow, width, and visibility are designated, even in the following equations and parameters. Similar equations exist for estimating capacities at staggered junctions and crossroads, with more reference to Siemens. The determination of queue lengths and delays is of central importance to assessing the adequacy of a junction. When actual entry flows are less than capacity, delays and queue sizes can be forecast using the steady state approach. With this method, as demand reaches capacity, delays and therefore queue lengths tend toward infinity. The steady state result for the average queue length L is shown in the following figure. In the aforementioned steady state equation, C is a constant depending on the arrival and service patterns. For regular vehicle arrivals, C is equal to 0. For random arrivals, C is 1. In the interests of simplicity, the latter case is assumed. Therefore, we can simplify the equation as follows. In reality, however, this is not the case with queue lengths where the ratio of flow to capacity reaches unity. Thus, at or near capacity, steady-state theory overestimates delays or queues. On the other hand, within deterministic theory, the number of vehicles delayed depends on the difference between capacity and demand. It does not take into account the statistical nature of vehicle arrivals and departures, and seriously underestimates delay, setting it at zero when demand is less than or equal to capacity. The deterministic result for the queue length L after a time t, assuming no waiting vehicles, is shown in the following. At a busy junction, demand may frequently approach capacity and even exceed it for short periods. Kimber and Hollis proposed a combination of equations using coordinate transformations to derive the following equations for average queue length and delay. For queue length, the following equation is derived. Next is the delay per unit time, followed by delay per arriving vehicle. And here are the parameters. For the example, capacities, queue lengths, and delays at a priority intersection will be identified. The flows are in passenger car units per hour. Here is the design reference flow. For the problem, we have to estimate the ratio of flow to capacity for each of the opposed movements and, for one of the highest ratio, estimate the average queue length and delay per vehicle during the peak hour. Here are the geometric parameters. The width of the major carriageway is 9.5 meters. The lane width for traffic exiting the minor road turning both left and right is 2.5 meters. The lane width on the major road for traffic waiting to turn right onto the minor road is 2.2 meters. Visibility to the right and left for traffic exiting the minor road turning right is 30 meters and 50 meters respectively. Visibility to the right for traffic exiting the minor road turning left is 30 meters. Lastly, the visibility to the right for traffic exiting the major road turning right onto the minor road is 30 meters. Here are the factored flows, and these are the parameters for D, E, and F, respectively. And next is the capacities. Ratios of flow to capacity. For the most critical movement, traffic exiting onto the major road, turning right, the ratio is just below the maximum allowed in urban areas of 0.85. The maximum reduces to 0.75 in rural areas. RFCs for opposed flow movements. It is important to take note that RFC values vary throughout a peak and can rise and fall sharply or slowly. The consequences of a high RFC depend on the flow. An RFC value of 1.2 might not matter with a very low flow, whereas a value of 0.8 might be disastrous with a high flow. This is the queue length at stream B to A. Next, we assume random arrivals, so we set C equal to 1. Next, we get the total delay during the peak hour by using the following equations. Next, we get the delay per arriving vehicle by following this process. It is important to consider that we are excluding the delay at stop line. we conclude that the average delay per vehicle is 1.3 minutes and the queue length is 5 vehicles, as indicated in the problem. Finally, we head to the geometric layout details, which consist of the horizontal alignment, vertical alignment, visibility, and dedicated lane on major road for right-turning vehicles. Horizontal alignment. In the ideal situation, the priority intersection should not be sited where the major road is on a sharp curve. Where this is unavoidable, it is preferable that the T-junction is located with the minor junction on the outside of the curve. Vertical alignment. The preferred location for a priority intersection is on level terrain, or where the gradient of the approach roads does not exceed an uphill or downhill gradient of 2%. Downhill gradients greater than this figure induce excessively high speeds because of gravity, while uphill approaches prevent the drivers from appreciating the layout of the junction. Dedicated lane on major road for right-turning vehicles. In the case of all non-simple junctions, provision of a right-turning lane, the lane itself, should not be less than 3 meters. It requires the provision of a turning length, a deceleration length, and a direct taper length. The next figure will illustrate these parameters for a Ghost Island junction. This is the following illustration. The turning length A is set at 10 meters. The deceleration length B varies from 25 meters to 110 meters, depending on the design speed on the major route. The taper C varies from 1 in 20 to 1 in 30 for Ghost Island or single-lane dualing intersections. Greater values are required for dual carriageway intersections.
Roundabout intersections. Roundabout intersection is a type of circular intersection or junction in which road traffic is permitted to flow in one direction around a central island, and priority is typically given to traffic already in the junction. It is also commonly known as rotunda. We have here some example of roundabout intersection that we can see in our place. So we have here the Fuente Osmeña. So the Fuente Osmeña gives uniform flow of vehicles from and to Osmeña Boulevard, General Maximum Avenue, and B. Rodriguez Street. Another example also is the Carcar City Rotunda, which was designed to maintain the good flow of traffic in N. Bacalso National Highway and San Vicente Drive. To control merging and conflicting traffic flows at an intersection, a roundabout performs the following two major functions. It defines the priority between traffic streams entering the junction, usually on the basis that traffic wanting to join the circulatory flow must give way to the traffic to the right already circulating in the roundabout. It also causes the diversion of traffic from its preferred straight line path, requiring drivers to slow down as they enter the junction. So this means that drivers who are about to arrive in the rotunda must make sure to give way to the vehicles who are already in the rotunda. After the lane is clear, they can now drive and follow the flow of traffic. And also, the driver should follow the required speed as they venture in the roundabout intersections in order to prevent accidents. We don't know how many vehicles will travel in the roundabout, that's why there is no specific traffic design that will maintain the flow of vehicles. Drivers only needs to be aware of the vehicles moving with them in order for the traffic to have a good flow. Roundabouts have difficulty dealing with unbalanced flows. As the number of arms increases, it will be much more complicated in maintaining the smooth flow of traffic on the roundabouts because of the increased number of vehicles going around and some drivers may strictly follow speed limit and appropriate driving. In situationals where flows are relatively well balanced and where 3 or 4 entry arms exist, runabouts cope efficiently with the movement of traffic. If the number of arms exceeds 4, efficiency may be affected by failure of drivers to understand the junction layout. It may also prove difficult to correct this even with comprehensive direct signing. So as what I've said earlier, it is really important to be aware in driving in the runabout sections, especially if there are many different intersections within the runabout. In addition to their ability to resolve conflicts in traffic as efficiently as possible, runabouts are often used in situations where there is a significant change in road classification or type, a major alteration in the direction of the road, and a change from an urban to a rural environment. So basically, runabouts are constructed in order to avoid traffic congestions, like for example, there is one or more intersections which crosses a driveway. This causes the traffic to be delayed or even will not move at all. If drivers will not give way. So in order for this issue to be solved, runabout intersections are applied so that there will be a smooth flow of traffic even if there are intersections within the driveway. So types of runabouts. We have 4 types of runabouts: the mini runabout, normal runabout, double roundabout, and other forms. So the mini runabout consists of a one-way circulatory carriageway around a reflectorized, flush, or slightly raised circular island less than 4 meters in diameter. Can be overrun with ease by wheels of heavy vehicles, domed to a maximum height of 125 mm at the center for a 4-meter diameter island. And mini runabouts are also used predominantly in urban areas with speed limits not exceeding 48 km per hour or 50 miles per hour. Mini runabouts are never used on highways with high speed limits because of the short distance between the entry points to the runabout. Drivers arriving at the intersection must monitor very closely the movements of other vehicles, both within the junction and on the approaches, in order to be in a position to react very quickly when a gap occurs. So as you can see in the picture, the mini runabout is a simple and small runabout. It is used in places where there are less vehicles, just like the provinces. So the second kind of runabout or type of runabout is the normal runabout. Runabout having a one-way circulatory carriageway around a curved central island at least 4 meters in diameter, with an inscribed circle diameter of at least 28 meters and with flared approaches to allow for multiple vehicle entry. So the number of recommended entry arms is either 3 or 4. If the number is above 4, the runabout becomes larger with the probability that higher circulatory speeds will be generated. In such situations, double runabouts may be provided as a solution. So we have here an example of a normal runabout. So compared to the mini runabout, normal roundabout is bigger, and we can clearly see the difference to it from the mini runabout by the triangular shaped center aisle seen in the exit or entrance of the runabout. Double runabout. A double runabout can be defined as an individual junction with 2 normal or mini runabouts, either contiguous or connected by a central link road or curved island. So it may be appropriate in the following circumstances: for improving an existing staggered junction where it avoids the need to realign one of the approach roads, and in order to join 2 parallel routes separated by a watercourse, railway, or motorway. It may be appropriate in the following circumstances: at existing crossroads intersections where opposing right turning movements can be separated, catering for junctions with more than 4 entries, and overloaded single runabouts where overall capacity can be increased by reducing the circulating flow traveling past critically important entry points. In situations where the double runabout is composed of two mini runabouts, the speed limit on the approaches must not exceed to 48 km per hour or must be 30 km per hour. So we have here an example of a double runabout. So the double runabout is much more complicated compared to the two previous runabouts. As the picture depicts, the double runabout was designed in order to achieve a good traffic flow of the vehicles and at the same time making use of it as part of the train railway. So lastly, we have the other forms. Other runabout configurations include two bridge runabouts, dumbbell runabouts, ring junction, and signalized runabouts. So these are runabouts which are designed uniquely based on how the traffic flows in a particular place. The design will make solutions in order for the traffic to have a good pace and at the same time having a safe driving on the runabout. So we have here an example. A major is to be constructed at the intersection of a single carriageway, two-lane road, deemed the minor road, and a two-lane dual carriageway, the major road. The annual average daily traffic, or the AADT, flow ranges predicted for each of the arms to the intersection in the design year, assumed in this case to be 12 years after opening. So as you can see, we have a major and minor lane which intersects with one another. The annual average daily traffic, or the AADT, of the major lane is 15,000 to 20,000, while the minor lane is 6,000 to 8,000. Taking the upper AADT flows of 20,000 for the major carriageway and 8,000 for the minor carriageway, the most appropriate form of junction is a roundabout. Using the AADT values, the average two-way annual average hourly traffic, or the AAHT, on all four approach roads can be computed by dividing each AADT value by 24. With the results, so we have here, so the 15,000 to 20,000 on a major lane was divided by 24 in order to get the annual average hourly traffic, and the result is 625 to 833 vehicles per hour. Same as with the minor lane, it was divided by 24 and the result is 250 to 333 vehicles per hour on the annual basis. As with the example, it is decided on economic grounds to design the junction to cater for the 30th highest annual hourly flow. On the basis of local traffic count data, it is found that the AAHT flow on each of the approach roads is translated into a design peak hour flow by multiplying by a factor of 3. So in order to get the design peak hour, the AAHT of the major and minor lanes are multiplied by 3. And the result is 1875 or 1,875 to 2,500 vehicles per hour in the major lane and 750 to 1,000 vehicles per hour in the minor lane. Directional splits derived from local traffic data are applied to these design flows in order to obtain the final directional flows. In this case, a 60-40 split in favor of entry flows from the southern and western approaches. So the 60-40 ratio was applied in the minor and major lanes. The 60 was designed for the vehicles coming from western part, which has 1,125 to 1,400 vehicles per hour, and southern part, which has 450 to 600 vehicles per hour, while the northern and eastern part is given 40, that is 750 to 1,000 vehicles per hour and 300 to 400 vehicles per hour respectively. Using information on local traffic flow patterns, turning proportions were deduced. So as you can see, the major lane has 0.6 turning proportion that is reduced into 2, and the minor lane is reduced from 0.5 to 0.25. Using these splits and taking the upper flow ranges, a set of design reference flows is derived which can be used to analyze the runabout intersection. So after the finalization of the design, it was approved that the final range flows of vehicles going to the runabout. For the vehicles coming from western part and approaching the runabout, it was implemented to have 300 vehicles per hour from 900 vehicles per hour. In the eastern part, from 600 vehicles per hour to 200 vehicles per hour. From the northern part, from 200 vehicles per hour to 100 vehicles per hour. Lastly, from the southern part, we have 300 vehicles per hour to 100 vehicles per hour. Traffic capacity at roundabouts. The design reference flows are derived from forecast traffic levels. The capacity itself depends mainly on the capacities of the individual entry arms. This parameter is defined as entry capacity and itself depends on geometric features such as the entry width, approach half width, entry angle, and flare length. So the predictive equation for the entry capacity, or the QE, used with all forms of mini runabouts or normal at grade runabouts is QE, which stands for the entry capacity into circulatory area, which is the vehicles per hour of the runabout, and it has a formula of K multiplied by the quantity of F minus FC QC. So where QC is the flow in the circulatory area in conflict with the entry, which is denoted as vehicles per hour, and K is 1 minus 0.00347 multiplied by the quantity of F minus 30 minus 0.978 multiplied by the quantity 1 over R minus 0.05, while F is the 303x and FC is equal to 0.21 TD multiplied by the quantity 1 plus 0.2x. Also, the TD is equal to 1 plus 0.5 divided by the quantity of 1 plus M, with M is equal to the exponent of parentheses with the d minus 60 over 10, and X is V plus quantity of E minus V over 1 plus 2S. Lastly, the S is 1.6 multiplied by the quantity of E minus V over LL. So these are the specific portions of the runabouts which are needed in order to entry capacity to be computed correctly. Each letters and symbols have values in relation to the runabout, which is used for calculation. So this equation is very useful in knowing the right design for the runabout. We have here its definitions, where E is the entry width in meters measured from a point normal to the near curb side. V is the approach half width measured along a normal from a point in the approach stream from any entry flare. And L prime is the average effective flare length measured along a line drawn at right angles from the widest point of the entry flare. While S is the sharpness of flare, indicates the rate at which extra width is developed within the entry flare. D is the inscribed circle diameter, the biggest circle that can be inscribed within the junction. F is the entry angle, measures the conflict angle between entering and circulating traffic. R is the entry radius, indicates the radius of the curvature of the near side curb line on the entry. So in these definitions, we will be using these definitions or the symbols and letters in the equation that we have mentioned earlier. So now in situations like incorporating grade-separated junctions, the F term is multiplied by 1.1 and the FC term by 1.4. So this equation can be used only if the roundabout design will have a grade-separated junctions. The only difference of this equation from the previous one is that the F and FCQC was multiplied by 1.1 and 1.4 respectively. So we have here the table and knowing the right or the allowable ranges of the different parts of the roundabout. So this table is very helpful in knowing the right measurements and designing the roundabout with a proper survey of the flow of vehicles in the area. Design reference flow. When analyzing the capacity of a roundabout intersection, the capacity of each of the entry arms is assessed and compared with the traffic flow expected at peak hours within the design year. If entry ratio of flow to capacity or the RFC of 70% occurs, queuing will be avoided in 39 out of 40 peak hours. All design reference flows are multiplied by 1.125 in order to allow for short-term variations in traffic flow at the roundabout within the peak hour. When analyzing the capacity of a roundabout intersection, the capacity of each of the entry arms is assessed and compared with the traffic flow expected at peak hours within the design year. So geometric details. The geometric guidelines for roundabout junctions are set out in TD 1693. The following are brief notes from TD 1693 regarding design of the following main parameters. We have the entry width, the entry angle, entry radius, entry deflection, inscribed circle diameter or the ICD, circulatory carriageway, and the main central island. So the entry width, TD 1693 states that it is good practice to add at least an extra lane to the lanes on the entry approach. So as the lanes in the roundabout becomes bigger, the flow of traffic will also be smoother. The entry angle, it is recommended that the entry angle should be between 10 and 60 degrees. So as the lanes in the roundabout of the following, the right entry angle will prevent traffic congestions. Entry radius. The absolute minimum radius should be 6 meters, and in order to cater for heavy goods vehicles, it should preferably not be less than 10 meters. This is also important so that vehicles, especially those with big trucks, will not have difficulty upon entering the roundabout since there is allotted space for them to maneuver. Entry deflection. This is one of the main determinants of safety on a roundabout, indicating the deflection to the left imposed on all entering vehicles. For each entry arm, the test radius of the entry path curvature, measured over a distance of at least 20 to 25 meters, should not exceed 100 meters. Entry deflection will ensure that all vehicles passing in the roundabout are safe since the curvature path is designed for safety purposes. The circulatory carriageway. The width of the circulatory should not exceed 15 meters and should lie between 1 and 1.2 times the maximum entry width. The chosen design sets the circulatory carriageway at 9 meters, approximately 1.2 times the maximum entry width value, which is 7.6 meters. Also, the circulatory lanes are designed properly so that there will be no accidents or traffic congestions that will occur as vehicles passes on the roundabout. Lastly is the main central island. The main central island will have a radius of 2 meters, the maximum allowable for an ICD of 28 meters, again to allow the safe movement through the junction of large articulated vehicles. In order to limit the circulatory carriageway, therefore, a low-profile subsidiary central island should be provided, extending the radius of the central island out of a total of 5 meters. The subsidiary island provides deflection for standard vehicles while allowing overrun by the rear vehicles of articulated vehicles. So this will be the center part where vehicles will be moving around it. It is also important in designing the roundabout since vehicles are moving in a circular motion. This also serves as the guide for the vehicles to move in a circular path.
Basics of traffic signal controls, optimization and delays. Traffic signals work on the basis of allocating separate time periods to conflicting traffic movements at a highway intersection so that the available carriageway space is utilized as efficiently and safely as possible. Priority can be varied with the time through the cycle of the signals. Within urban areas in particular, in situations where a road has a number of intersections along its entire length, signal linking can be used as a method for allowing almost continuous progression of traffic through the route. So the installation of traffic signals is justified by the need to reduce delay to motorists and pedestrians moving through the junction, reduce accidents at the junction, improve the control of traffic flow into and through the junction in particular, and the area in general, thereby minimizing journey times, and impose certain chosen traffic management policies. Traffic signals can, however, have certain disadvantages. They must undergo frequent maintenance along with frequent monitoring to ensure their maximum effectiveness. There can be inefficiencies during off-peak times leading to increases in delay and disruption during these periods. Increases in rear-end collisions can result, and signal breakdown due to mechanical or electrical failure can cause serious interruption in traffic flow. Phasing at signalized intersection. Phasing allows conflicting traffic streams to be separated. A phase is characterized as a sequence of conditions applied to one or more traffic streams. During one given cycle, all traffic within a phase will receive identical and simultaneous signal indications. For example, crossroads intersection, where north-south traffic will conflict with that traveling from east to west. Since the number of conflicts is 2, this is the number of required phases. And for the other more complex intersections, more than 2 phases will be required. The control of traffic movement at a signalized junction is often described in terms of the sequential steps in which the control at the intersection is varied. This is called stage control, with the stage usually commencing from the start of an amber period and ending at the start of the following stage. In Figure 5.28, we have the typical stages within a two-phase system. So since this is a two-phase system, we have 2 stages, stage 1 and stage 2. So in stage 1, the north to south is green and the east to west is red, while stage 2, the north to south is red and the east to west is green. And in the Figure 5.29, this is the typical stages within a 3-phase system, in which 2 lanes each direction with a dedicated lane for right-turning vehicles in all cases. So we have stage 1, stage 2, and stage 3. So in stage 1 and stage 2, the north to south is green, while in stage 3, the north to south is red. And in stage 1, there is no right turn, and stage 2, right turn only, and then the stage 1, east to west is red, same as with stage 2, and in stage 3, the east to west is green in all movements. So now we have saturation flow. The capacity for each approach to an intersection can be estimated by summing the saturation flows of the individual lanes within each of the pathways. The main parameters relevant to the estimation of capacity for each approach are number, width, and location of lanes. The overall capacity of an approach road is equal to the sum of the saturation flows for all lanes within it. It is assumed that the average lane width on the approach to a signalized intersection is 3.25 meters. At this value, assuming zero gradient, the saturation flow for near-side lanes is set to 1,940 passenger car unit per hour, increasing to 2,080 passenger car unit per hour for non-near-side lanes. Weather conditions. In wet weather conditions, saturation flows decrease to 6% below their dry weather values. Gradient. For every 1% increase in uphill gradient, measured over 60-meter distance back from the stop line, the saturated flow value will decrease by 2%. Downhill gradients do not affect saturation values. Lastly, we have turning movements. In situations where the turning traffic is unopposed, saturation flows will decrease as the proportion of turning traffic increases. Where turning traffic is opposed, the saturation flow will depend on the number of gaps in the opposing traffic flow, together with the amount of storage space available to those vehicles making this traffic movement. There are equations derived by Kimber et al. In 1986 for predicting saturation flow. In an unopposed traffic streams, the saturation flow is given by the equation of S sub 1 is equal to S sub 0 minus 140 d sub n, where d sub n is equal to 1 if this is a near side lane, or 0 if this is a non-near side lane, divided by 1 plus 1.5 times f, in which f is the proportion of turning vehicles in the lane under scrutiny, divided by r, which is the radius of curvature of vehicle path in meters, in which the saturation flows unit will always be passenger car unit per hour. S sub 1 will be the equation 5.24. So where S sub 0 is equal to 2080 minus 42 d sub g, wherein d sub g is equal to 1 if this is uphill entry roads, or 0 which is the downhill entry roads, times g, which is g is the percentage gradient of entry road, plus 100 times w, which is the entry road lane width in meters, minus 3.25. So the S sub 0 will be the equation 5.25. So now we have the opposed traffic streams. So in this instance, the saturation flow in a given lane for right-turning opposed streams is given by the equation of S sub 2 is equal to S sub g plus S sub c. So this will be our equation 5.26. So the two components of this equation, which are S sub g and S sub c, are computed as follows. So in S sub g, this is the saturation flow occurring during the effective green time within the lane of opposed mixed turning traffic. So we have a bunch of equations here. So S sub g is equal to S sub 0 minus 230 divided by 1 plus big letter T minus 1 times f. So this will be our equation 5.27. So for the big letter T, it is equal to 1 plus 1.5 divided by r plus small letter t sub 1 divided by small letter t sub 2. So this will be the equation 5.28. So in the next equation, we have the small letter t sub 1, which is equal to 12 times x sub 0 squared divided by 1 plus 0.6 times 1 minus f times n sub s, in which x sub 0 is the degree of saturation on the opposing entry arm, or the ratio of flow to capacity, and the n sub s is the number of storage spaces within the junction which the right-turning vehicles can use so as not to block the straight-ahead stream. So this will be the equation 5.29. So for the next is the x sub 0. This is equal to q sub 0 divided by lambda times n sub 1 times s sub 0. So q sub 0 is the actual flow on the opposing arm measured in vehicles per hour of green time. Then the lambda there is the effective green time divided by the total cycle time, or C. Then the small letter n sub 1 is the number of lanes within the opposing entry arm. And the small letter s sub 0 is the saturation flow for each of the lanes in the opposing entry arm. So this will be our equation 5.30. So the next is the small letter t sub 2, which is equal to 1 minus f times x sub 0 squared. So this will be our equation 5.31. So now we have S sub c. S sub c is the saturation flow occurring after the effective green time within the lane of opposed mixed turning traffic. So the difference between S sub g and S sub c is that S sub g is when the saturation flow occurs during the effective green time, while the S sub c occurs after the effective green time. So the equation for S sub c would be big letter P times 1 plus n sub s times f times x sub 0 times 0.2 times 3600 divided by lambda times c, where P is the conversion factor from vehicles to passenger car units. So this will be our equation 5.32. So for the next equation, we have the big letter P. So this is equal to 1 plus a summation of a sub I minus 1 times small letter p sub I, where a sub I is the passenger car unit value of vehicle type I, and the small p sub I is the proportion of vehicles of type I. So this will be our equation 5.33. So the passenger car unit values used in connection with the design of a signalized junction are given in table 5.6. So we have the vehicle type and the passenger car unit equivalent. So for example, this will be the calculation of saturation flow for both opposed and unopposed traffic lanes. So the approach of road shown in figure 5.30 is composed of two lanes, both 3.25 meters wide. The near side lane is for both left turning and straight ahead traffic, with a ratio of 1:4 in favor of the straight through movement. The non-near side lane is for right turning traffic. This movement is opposed. The degree of saturation of the opposing traffic from north is 0.6. So we have the figure 5.30 here, which is the diagram of two-lane approach. So the turning radius for all vehicles is 15 meters. Zero gradient and 1/32 effective green period per 60-second traffic cycle can be assumed, in which lambda is equal to 0.5. So the traffic is assumed to be composed of 90% private cars and 10% heavy commercial vehicles. So calculate the saturation flow for each of the two movements. Assume the two storage spaces exist within the junction. Okay, so solution. For the near side lane, the saturation flow can be calculated using equations 5.24 and 5.25. So these equations are the S sub 1 and the S sub 0. So the values of the relevant parameters are D sub n, which is equal to 1. 1 because this is the near side lane. So we have F is equal to 0.2, R is equal to 15, G is equal to 0, and W is equal to 3.25. Then we substitute this to our equation 5.25, the S sub 0, so that we will be able to get the S sub 1. So since we got the S sub 0, then we are able to compute for the S sub 1, in which the answer is 1,902 passenger car unit per hour. So for the non-near side lane, the saturation flow can be calculated using equations 5.26 to to 5.33. So we have f, which is 1 since all vehicles are turning. Then x sub 0 is equal to 0.6. N sub s is equal to 2 since there are 2 existing storage spaces. Then we will solve for t sub 1, in which we will substitute the numbers, and then we will be able to get 4.32. And then for t sub 2, substitute everything, and then 0.64. The big letter T, we have 7.85. The S sub G, now we have 236 passenger car unit per hour. And for the big letter P, we have 1.13, and for the S sub C, we have 367 passenger car unit per hour. So therefore, S sub 2, we will add S sub G plus S sub C, which is 236 plus 367 is equal to 603 passenger car unit per hour. Then we move on to effective green time. Effective green time is defined as the length of time that would be required to get a given discharge rate over the stop line if the flow commenced and finished simultaneously and instantaneously on the chain passenger car unit per hour. Then we move on to effective green time. Effective green time is defined as the length of time that would be the discharge of vehicles across the stop line starts at the beginning of the green period and finishes at the end of the amber period. The intervals of time between the start of actual green time and the start of effective green, and between the end of effective green time and the end of the amber period, are termed lost time. So we have figure 5.31 here. It can be seen that the actual green time plus the amber period is equal to the effective green time plus the 2 periods of lost time at the beginning and end of the cycle. So normally the lost time is assumed to be taken as equal to 2 seconds with the amber time set at 3 seconds. Effective green time is thus equal to actual green time plus 1 second. So now we have the optimum cycle time. Assuming the signal, normally the law on fixed time control, the cycle length will directly affect the delay to vehicles passing through the junction. If the cycle time is short, this lost time becomes a significant proportion of it, leading to inefficiencies in the working of the junction and consequent lengthy delays. So Webster, in 1958, developed a set of formula for establishing the optimum signal settings in order to minimize the total. If the cycle time is short, this lost time becomes a significant proportion of it, leading to inefficiencies in the working of the junction and consequent lengthy delays. So Webster, in 1958, L is the total lost time per cycle, and Y is the sum of the maximum Y values for all the phases which make up the cycle. So this will be the equation 5.34. So there is a minimum cycle time of 25 seconds based on safety considerations. A maximum cycle time of 120 seconds is considered good practice. Normally, the cycle time will lie within the range of 30 to 90 seconds. So the lost time. Lost time per cycle consists of the time lost during the green period plus the time lost during what is known as the intergreen period. The intergreen period provides a suitable time during which vehicles making right turns can complete their maneuvers safely, having waited in the middle of the intersection. The period of time lost to traffic flow is referred to as lost time during the intergreen period. So we have table 5.7, which shows an example of a two-phase system. This is the typical intergreen period within a two-phase signal system, which we have phase 1 and phase 2. So in the middle is where the 5 seconds intergreen period, which this is 3s plus 2s, because this is the amber period plus the lost time period. So example, in the calculation of optimum cycle time, the actual and saturation flows for a three-phase signal system are detailed in Table 5.8. The phasing details are given in Figure 5.32. The intergreen period is set at 5 seconds, the amber time at 3 seconds, and the lost time due to starting delays at 2 seconds. Calculate the optimum cycle time for this intersection. So in Table 5.8, this is where the actual flows, saturation flows, and Y valuations. So the numbers with asterisk are the maximum values. And also we have Figure 5.32, which is the staging diagram, and we have 3 stages. So, solution. The 3 phases for the intersection in question, together with the movements for each of the individual approaches are: in stage 1, we have approach 1A, approach 1B, approach 1C, and approach 1D, where in approach 1A is the north or south movement, same as with 1B, and the 1C and 1D is the south or north movement. However, approach 1A and approach 1C are straight ahead and left turning, while the approach 1B and approach 1D is right turning. In stage 2, we have approach 2A and approach 2B. So in approach 2A, we have east or west movement, in which this is straight ahead and left turning. In approach 2B, we have west or east movement, which is straight ahead and left turning. So in stage 3, we have approach 3A and approach 3B. So in approach 3A is east or west movement, right turning, and the approach 3B is the west or east movement, right turning. So for each approach, the maximum Y value is marked with an asterisk in Table 5.8. So in stage 1, the maximum Y value is 0.25, same goes with stage 2, and in stage 3 is 0.22. So for each of the 3 phases, the lost time due to starting delays is 2 seconds, as is the lost time during the intergreen period. The total lost time is therefore 12 seconds, since 4 times 3 seconds is equal to 12 seconds. So the optimum cycle time is calculated as follows. So we are going to use the equation 5.34. So C sub O is equal to 1.5 L, in which L is 12 seconds, since the total lost time is 12 seconds, plus 5 divided by 1 minus Y, where Y is equal to the total number of maximum values of Y, in which this is 0.72. So since we have L and Y, we can be able to compute the optimum cycle time. So C sub O is equal to 82 seconds. Then we have the average vehicle delays at the approach to a signalized intersection. So Webster in 1958 derived the following equation for estimating the average delay per vehicle at a signalized intersection. So D, which this is the average delay per vehicle, is equal to C times 1 minus lambda to the power of 2 divided by 2 times 1 minus lambda times x plus x squared over 2q times 1 minus x minus 0.65 times c over q squared to the power of 1/3 times x times 2 plus 5 lambda. So this equation would be equation 5.35. So where c is the cycle length, lambda is the effective green time divided by cycle time, q is the flow, s is the saturation flow, and then the x is q over lambda times s. So the first term in equation 5.35 relates to the delay resulting from a uniform rate of a vehicle arrival. The second term relates to the delay arising from the random nature of vehicle arrivals. And the third term is an empirically derived correction factor obtained from the simulation of the flow of vehicular traffic. So, the above formula can to the delay resulting from a uniform rate of a vehicle arrival. The second term relates to the delay arising from the random nature. So, this will be the equation 5.36, where A is equal to 1 minus lambda squared over 2 times 1 minus lambda x, then B is equal to x squared over 2 times 1 minus x. And the C is the correction term, which can be taken as 10% of the sum of the first two terms. So the equation 5.35 can thus be written in approximate form as D is equal to 0.9 times C times A plus B over Q. And this will be our equation 5.37. Now we have an example for the calculation of average vehicle delay at the approach to a signalized junction. An approach has an effective green time of 65 seconds and an optimum cycle time of 100 seconds. The actual flow on the approach is 1,000 vehicles per hour, with its saturation flow estimated at 1,750 vehicles per hour. Calculate the average delay per vehicle using both the precise and approximate formula. So in the solution, we have C is equal to 100 seconds, lambda is equal to 0.278 vehicle per second, S is equal to 0.486 vehicle per second, and the X, we have 0.88. So using the formula, the equation of 5 in 5.36, we will be able to get the A, B, and C. So we can answer using the precise formula, in which this is the equation 5.35. So we have 22 seconds. So in using the approximate formula, we are using the equation 5.37, and the result, we have D is equal to 23 seconds. So for average queue lengths at the approach to a signalized intersection, it is normal practice to estimate the queue length at the beginning of the green period, as this is the instant at which it will be greatest. If the approach is assumed to be unsaturated, then whatever queue forms during the red period will be completely discharged by the end of the green period. Where this is the case, the maximum queue formed is equal to the product of the actual flow and the effective red time for the approach. So the formula for the unsaturated case is therefore N sub U is equal to Q times R. This will be our equation 5.38, where N sub U is the queue length at the commencement of the green period, Q is the actual flow rate, and the R is the effective red period, which is the cycle time minus the effective green time. So if it is assumed that the intersection is at a saturated level of flow, the queue length will vary gradually over any given interval of time. The average queue length can thus be estimated as the product of the actual flow Q and the average vehicle delay D. To this value, an estimate accounting for cyclical fluctuations caused by short-term variations in flow during the red and green periods must be added. These can range from 0 to QR, Therefore, an average value of QR divided by 2 is taken. So, combining these two terms, an expression for the saturated case is N sub S is equal to Q times D plus 1/2 QR, where N sub S is the queue length at the commencement of the green period, and the D is the average delay per vehicle on the approach. So this equation will be equation 5.39. So at the minimum, in this case, D will equal R over 2. Therefore, the equation for the saturated case reduces to that for that unsaturated case, especially N sub S is equal to QR. Since this is the minimum value of N sub S, equation 5.39 can be adjusted as N sub S is equal to Q times D plus 1/2 QR or QR, whichever is greater. So we have example here for the calculation of average queue length at the approach to a signalized junction. So taking the figures from the previous example, calculate the average queue length at the approach. So for the solution, we have C is equal to 100 seconds, Q is equal to 0.278 vehicle per second, R is 35 seconds, and D is 22 seconds. So therefore, taking the saturated case, N sub S is equal to Q times D plus 1/2 QR or QR. So substitute everything, and then we have 10.98, then round up, we have 11, and the other one is 9.73, we have 10. So we have to choose which is greater. So since 11 is greater than 10, so the answer is 11 vehicles. So last, we have then round up, we have 11, and the other one is 9.73, we have 10. So we have to choose which is greater. So since 11 is greater than 10, so the answer is 11 vehicles. To the preceding signals, and in the ability of a significant platoon of traffic passing through the entire set of intersections without having to stop. So one method for achieving this coordination is through use of time and distance diagram, with time plotted on the horizontal axis and distance on the vertical axis. So in order to construct the diagram, each intersection is examined individually and its optimum cycle time computed. The one with the largest required cycle time, which is called the key intersection, is identified and taken up as the cycle time for the entire network, or C1. Knowing the lost time per cycle, the effective green time and hence the actual green time for the key intersection can be computed. So with regard to the other non-key intersections, the maximum actual green time in each case is derived through determination of the smallest acceptable green time for the minor road phases. So the minimum effective green, which is in the minor route, is equal to the y side times c sub 1 divided by 0.9. So this equation would be the equation 5.40. So the minimum actual green time for the side or minor roads can then be calculated by addition of the lost time per phase and subtraction of amber time. So as stated earlier, actual time is 1 second less than effective time. So by subtracting this value from the cycle time plus the intergreen period, the maximum actual green time permitted for the junction in question along the main axis of movement can be calculated. So now we have an example for the calculation of time and distance diagram. Three two-phase signalized intersections are spaced 400 meters apart. The main axis of flow is in the north or south direction. Details of the actual and saturation flows at each of the junctions are given in Table 5.9. The starting delays are taken as 2 seconds per green period. The amber period is 3 seconds in all cases, and the period during which all lights show red during a change of phase is 2 seconds. Locate the critical intersection, calculate the minimum and maximum actual green times, and outline the construction of the time-distance diagram indicating how vehicles will progress along the main axis of flow. So the junction is illustrated diagrammatically in figure 5.33. So for the solution, intergreen period is equal to 10 seconds, which this is 5 seconds per phase, 3 seconds amber plus 2 seconds red. So lost time is equal to 8 seconds in total per cycle, which this is 4 seconds per phase, 2 seconds starting, and 2 seconds during intergreen. So firstly, the optimum cycle time for each intersection must be calculated applying equation 5.34 to the 3 sets of data in table 59. So we have the equation 5.34 here, and then the values of y critical for each intersection in the network are indicated in table 5.9. So here in table 5.9, we have the critical ratios for each intersection in the network. We have the intersection A1, A2, and A3. So based on the critical ratios in table 5.9, the optimum cycle time for each intersection can be computed as: in junction A1, the optimum cycle time is equal to 94 seconds. Junction A2 is 104 seconds, and in junction A3, we have 70 seconds. So we also have here a figure, in figure 5.33, a diagrammatic layout of network of urban-based intersections. So from the above figures, it can be seen that the longest of the 3 cycle times is for junction A2, which is 104 seconds. So this is the key junction and is thus adapted for the entire network. So next, we will find the minimum actual green time. So, assuming a cycle time of 104 seconds, the effective green time can be estimated along the main north or south axis by the use of the y critical values of junction A2. Of the 104 seconds, 8 seconds is lost time. Therefore, the combined effective green time in both directions is 96 seconds, in which 104 seconds minus 8 seconds. So the relative values of the critical ratios are then used to estimate the proportion of this green time allocated to the north, south, and east or west direction. So since the y critical of the north-south is 0.363 and the y critical of the east-west is 0.474. So using the formula, we have 96 times 0.363 over 0.363 plus 0.474 equals 42 seconds. So given that starting delays are 2 seconds and the amber time is 3 seconds, the actual green time is equal to the effective green time minus 1 second. So the minimum actual green time, or N over S, is equal to 42 minus 1. So this is 41 seconds. So this figure is adopted as the minimum green time for the remaining 2 junctions within the network, the A1 and A3. So next, we will find the maximum actual green time. So the upper limit for actual green time at A1 and A3 is computed by consideration of the minimum effective green time required by traffic at these junctions along their east-west axis, termed side traffic. So the minimum effective green time of the east-west is equal to C sub I times y critical of the east-west divided by 0.9. So we have the answer of 116 times y critical of the east-west. So for both A1 and A3, the y critical of the east-west is 0.444. So the answer for this would be 116 times 0.444 equals 52 seconds. So again, given that the starting delays are 2 seconds and the amber time is 3 seconds, the actual green time is equal to the effective green time minus 1 second. So 52 seconds minus 1, then the minimum actual green time of the east-west is 51 seconds. So the total actual green time for both the north-south and east-west phases is 94 seconds, estimated from the subtraction of the intergreen period 10 seconds from the total cycle time 104 seconds. Subtracting the minimum actual green time along the side route from this figure yields the maximum actual green time along the main north or south axis. So therefore, for both A1 and A3 intersections, the maximum actual green time for north-south is equal to 94.51 seconds, in which this is 43 seconds. So next, assuming a speed of 30 kilometers per hour, which means that it takes a vehicle just under 48 seconds to progress from one junction to the next. Knowing this together with the minimum and maximum actual green times, which is 41 seconds and 43 seconds, the time or distance diagram illustrating the ability of vehicles to progress in both directions through the network of intersections can be compiled. So, an illustration of the time distance diagram for the above example is shown here in figure 5.34. So note that the vehicles travel between junctions during approximately half the cycle time. So here in figure 5.34, we have the illustration of time distance diagram for this example.